Yeah, thank you for the introduction. So, it has been a very nice workshop. And in my talk, I will continue on the uncertainty principle, but actually we'll go way back to somewhat the beginning of we'll also be considering Hardy's uncertainty principle, but actually in a very specific case of isotropic time frequency decay related to the Gaussian. But what we'll do is find some very quantified results when we know we have a type of time frequency decay, how we can measure it using the Hermite coefficients. Okay, so let me get no idea. Okay, so okay, let's just first fix constants. I'll define the Fourier transform in this way. And then we have the classical result from 1933 from Hardy. Okay, I've been a bit sloppy because actually I put it in multiple dimensions, but he showed it in one dimension. Well, if we so if you remember in the previous talk, where you had the A and the B, which measured differently in the time frequency decay, but now if we put it together and then we have some form of isotropic time frequency decay, then we have the result that if you have this Gaussian decay with some parameter eta in both the function and its Fourier transform, then we know that if this eta is strictly larger than 1/2, the function should vanish. But if it is 1/2, then we actually know it's some is the Gaussian multiplied by some complex number C. Okay, but actually what Hardy already did in his paper was also show that when we know we have a bit of larger bounds here on the time frequency decay, we can say somewhat more. Namely, if you introduce, as we all know, the Hermite functions, which are eigenfunctions of the Fourier transform, so which already give you some notion that they might have a good isotropic time frequency decay, then we know that if the function has this Gaussian decay, but multiplied by some polynomial of some degree n, again isotropic in its time frequency decay, then we know that the function, this holds if and only if this function belongs to the linear span of all of the Hermite functions. Okay, so we already showed that in that point. But now the question comes, okay, so now we have these finite combinations of these Hermite functions. What if we allow some more, if we look at the span of these functions in a somewhat larger space, so if we look at the coefficients of the Hermite functions applied to the f, if we know some certain of bounds on this, so if we have a sort of quantified version on the Hermite functions, the bounds there, do we also have quantified time frequency decay related to the Gaussian? Okay. Now, of course, we know that the Hermite functions, they form an orthonormal basis for L2. So, yeah, typically we have this decomposition of f in the parameters of little L2. And of course, note that because of they are eigenfunctions of the Fourier transform, we note that the absolute value of the function or its Fourier transform of the Hermite coefficient doesn't matter so much. But what we also have, of course, here in this general context of the Hermite function is this nice transform allowing us to map L2 into the Fock space using the Bartman transform and having then its expansion using the Hermite coefficients of F. Okay, and actually we have an integral transform representation of this transform here, but of course you can also define it like this into the Fock space, which has this Gaussian decay with respect to the complex parameters. Okay, but then let's look at time frequency decay. So the Hermite functions, this during the last century, and actually up until like recent results even, it has been shown that the Hermite functions form an absolute Schauder basis for the following functions, which I'll now represent using time frequency decay. But actually, why all of these results work here is because they also have a differentiable or even ultra-differentiable representation. So Schwarz already showed in his work that the Schwarz space he introduced can already be detected using the Hermite functions, namely, so if you have this faster decay, if you multiply by any polynomial, we can detect this exactly as having this kind of bounds on the Hermite functions. Okay, so this was already in his work in Théorie de Distribution. And then further, of course, now if we try to specify more the time frequency decay, as Galfand and Shilov did in their work, because this can be useful looking at, for instance, certain of PDEs when you have more regularized and more ultra-differentiable types of functions. It was actually already in 1963 that Zhang also noticed that if you have this very fast time uniform isotropic time frequency decay up with some parameter 1 over s, where s is at most should be at least 1.5, then this can also be detected using the Hermite coefficients again. Okay, and this is for some eta, and then actually more than 20 years later, this result was rediscovered by Filipovic, but he also looked at the Galfand-Shilov subverting time, where you have this for every eta, you have this time frequency decay. Then again, we can detect this using the Hermite coefficients. All right, and like I said before, actually, that we have this time frequency decay is not how they initially did it. They did it using ultra-differentiability, but then later, like 10 years later from here, we also saw that this, but actually it's already contained in Galfand and Shilov's work, that this is equivalent to the time frequency. Okay, and then actually in a very nice paper from Langenbruch in 2006, he considered a very general case where we have Fourier invariant Galfand-Shilov spaces, which means that we weigh it using some kind of weight sequence having certain conditions, but still being above the minimal space that we can have that is Fourier invariant and having this almost Gaussian decay. He actually showed that we can also characterize this. I just put this on the slide. I'll not go too much in details, but I would strongly recommend, if you want to look at any of these results, to look at his paper, because he gives some very, very nice, very precise estimates. Okay. So we see that these very nice spaces we've seen that are somewhat started with Schwarz space, but then generalizations of these spaces that go more specific into the certain type of time frequency decay can be detected using the Hermite coefficients, but actually we somehow made a jump. So we went first from the Gaussian and then the linear span of the Hermite functions, and then we jumped to the Schwarz space and went down again to more and more specified time frequency decay. But the jump, it was just made so that we have like these kind of ultra-differentiable or differentiable descriptions of these spaces, okay? But what if we now want to close the jump we made and still look at very specified time frequency decay that not necessarily has these descriptions or these spaces we had here? And actually, this was an idea that I think Joachim actually started with, is that, okay, if we consider the smallest Fourier invariant Galfand-Shilov space, so S1/2, Galfand and Shilov showed that you cannot lower the parameter 1/2, or you'll also have a trivial function. So we have this description here. Then Zhang showed that, okay, these are exactly the spaces such that the Hermite coefficients have this kind of decay for some R. Then, all right, what if we just change the parameter? What if R can be chosen arbitrarily small? And this then naturally leads to a new kind of space we could have, which we call the first and largest proper Filipovic space. So we say that F, so this is a somewhat abstract definition, F belongs to this space if you have for each R the Hermite coefficients have this kind of decay. All right, and of course this is a non-trivial space, contains all of the Hermite functions, so we're not working on something empty. Okay, and we have this kind of decay, but of course you can have more specified decay like this, but we leave the situation of the Galfand-Shilov spaces right here. But these spaces became known as the Filipovic spaces, somewhat in honor of Filipovic and his results. And these, in the past more than 10 years, have been applied in various contexts. For instance, they can be shown to show well-posedness of the Schrödinger equations, where it's ill-posed, for instance, for the Galfand-Shiller spaces and their dual. So they actually are allowed, because of this very nice decay in the Hermite coefficients, are able to solve problems we couldn't do before. They also appear in the study of tuplets and pseudo-differential operators, but what also for me personally somewhat found special about these spaces, they are automatically Curtis sequence spaces, so topologically they possess very strong properties, okay? And that's actually why earlier Langenbruch did his results, because if you have, when you have this kind of structure that is actually just a weighted sequence space, then you can apply this in various abstract functional analytical parts. So you automatically have nuclearity, you have kernel theorems. You look at partial differential equations on your spaces and then see, for instance, when does this have a linear right inverse? These are all things that come automatically when you have this type of Curtis sequence spaces. These are like somewhat the optimal spaces for this. So in a sense, these spaces are somewhat, by design, made to be good extensions of the Galfand-Shiller spaces. However, for a real proper analysis, they also lack some algebraic properties that the Galfand-Shiller spaces had. For instance, they're not invariant in dilation, multiplication, and convolution. Just look at the Gaussian already. This will go wrong. All right. So on the one hand, we have these nice spaces that have these very good properties that we can apply them. But on the other hand, it's somewhat difficult to work with them. So somehow you would like to know, do you have a more natural characterization of these spaces that are just not, okay, they have these Hermite coefficients that decay nicely. Okay. And then work started on this. And for instance, let me now discuss the example of the largest one. First of all, as I said before, the Barkman transform, this has this very natural mapping of the Hermite coefficients to these analytic functions that are expansions using these coefficients. Then one shows quite directly that actually this belongs to this Filipovich space if you have these bounds on the Barkman transform for any lambda. Okay. Another way that it might give you some more info is that if you, for instance, look at the harmonic oscillator, then you can detect these functions by just looking at the iterates of the harmonic oscillator applied to the function. If this has certain bounds, then we know it's in the Filipovich space. But still, somewhat, I would say, abstract. But then, maybe because remember where we're coming from. We're coming from the Gaussian, in essence, and the Hermite functions. These have this very well-defined time-frequency decay. Can we not just describe these functions in sense of the function and the Fourier transform? Okay. And the first result in this direction came by Joachim Gumber in 2023. And it was shown that if your function belongs to, for instance, the largest Filipovich space, then we have this time frequency decay here. Okay, so we can go, this lambda is like a kind of error term that goes to the Gaussian, all right? And this can be chosen arbitrarily small, right? So if we have the Hermite coefficients, have these bounds, then we have the time frequency decay. But now, to go back in this work, at first we still needed more information to go back. We needed the fractional Fourier transform, needed more estimates on several directions. Somehow, this seemed like a natural condition to go back, but yeah, it was fighting back. But then, not so recently, we could show that in the one-dimensional case, this actually characterizes fully this space, but also other spaces. And not so long ago, actually, we were able to show the multidimensional case. And again, this required some more work, but all of the work that was needed was somehow in complex analysis. So we first needed to translate everything and then develop some tools that could handle the things we needed. Okay, so let me give a bit of an overview on how we got to this. So So, and I think this gives a very natural description of these spaces. And somewhat extends Hardy's results, I think, in optimal sense. So first, I want to weigh. How can I weigh time frequency decay, but also these Hermite coefficients in a uniform way? And remember, like I word before, somehow this is very closely related to ultra differentiability and the theory there. So we use some tools from there. And here I will just say a weight function, omega, is just an unbounded, non-decreasing function from 0 infinity to 0 infinity. And then I want to impose at least as few conditions as possible. So I'll just ask that it has some kind of moderateness. This is just that it's translation invariant, these spaces, or that you can somewhat take convolution in the Bachmann side. Okay? This just says that if you have omega of a sum, it's bounded by some constant times the sum of those. Okay, or equivalently this. And then a somewhat more important condition that can connect bounds on Hermite coefficients with the decay is what we call, or what is called the delta condition. It's not just to, in our context, we don't ask the omega to be convex, but just omega to the e to the power x is convex. And then we can take the Young conjugate of this function phi, which is this omega e to the x. And remember, the Young conjugate actually gives you some, like, the conjugate physical property of something. So if you go from space, you will go to momentum and stuff. So this is how we can connect these time frequency decay with these parameters. This is ultra differentiability parameters. Okay? And one note here to make is that either your omega, if you have this delta condition, either your omega is just equivalent to the logarithm, or we know it's bound. The logarithm is little o of your omega. All right, so we'll use these, and then very quickly, first let me introduce, of course, now. So we have the Pilipovich spaces that we, in general, define using these weight functions. Okay, so we'll, for now, just define them as these L2 functions whose Hermite coefficients have this somewhat horrible-looking bounds. Okay, but we're using our phi star, and then you can either take the union or the intersection, but maybe some examples for certain types of weight functions. So the smallest one, this actually just gives you, depending on when you take the union or the intersection, that there can be only a finite amount non-zero. Okay, so this is the smallest space. This is what we would correspond to the smallest space, so the linear span of the Hermite function. Okay, but if you go a bit further, you take the logarithm of some power, then we already get something non-trivial here. And then you can even go further, take power polynomials, for instance, x to this power, and then you will get these coefficients you can calculate easily. And then finally, the biggest one, x squared. You get this. All right. But then very quickly, you show without much effort that if you have a weight function satisfying delta, then an entire function is the image of the Bachmann transform of some L2 function coming from the Pilipovich space if you have this bound here on the Bachmann transform. Okay? So these are actually gives you a correspondence between the Pilipovich spaces and kind of weighted Hermander algebras. All right, good. And now that we have this direct connection between these spaces, these entire functions, and the Pilipovich spaces, let's now connect it to time frequency decay. And therefore, we use, as one would expect, a short time Fourier transform. Okay, but we'll use it just with the window Gaussian, normalized Gaussian. Okay, so as we know by now, I think by the end of this week, what it is this windowed form of the Fourier transform. And then we have three nice properties that we have to use. First of all, if we have decay on our function, we can get decay on our Fourier transform, then we'll get decay on the short time Fourier transform. But we can also go back by using the Fourier inversion formula. If we know something on the short time Fourier transform, then we can get it to the actual function using this formula. But then the special thing about it all is, of course, the connection between the Bachmann transform and the short time Fourier transform, which is given by this. Okay? So in this way, if you know something about time frequency decay, we'll know something on the Barkman transform and just know when they are in these weighted spaces and vice versa. Okay? So using all of this, I'll maybe show everything. Okay. So using this, we already could get to here. Okay, so we have a weight function bounded by, of course, slower than the x squared, or depending on the case we're working in, but then we have these series of implications. Namely, we are in the Filipovich space corresponding to the weight function, or we have this Barkman bound. This is the equivalent as we saw. And then from the Barkman transform, we can go back to the actual time frequency decay that we want. So we have this Gaussian decay plus something a little bit bigger. Okay. And if we have the time frequency decay, we can go back to the Barkman transform, but not fully, because we can only use it separately, the time and the frequency decay. So we cannot fully go back to step 3 at this moment. Okay, just knowing this. We do get this bounce where we have already what we want either on the frequency or the time, but then we have this extra error term, this Gaussian bound here. Okay. But note, and this is the important part, that actually if we look at only real parts or imaginary parts, we already have what we want. Okay, so we just need to close those. But this is not sufficient to know. We actually know that we have to have these bounds for everything to work. So how do we close? If you remember a bit from analysis, you have what the Bragman-Lindelof principle. So let me first state it in the classical form. Okay, if you have some sector with some angle rho, and now, yeah, okay, note first of all, we're working in dimension 1 here, but if you have this angle rho and you have a parameter sigma, then if you have an analytic function on this angle, on this sector with angle pi over sigma, with continuous extension to its border, and moreover on the border you have boundedness, and you have this boundedness in the sector with respect to the sigma. So for every epsilon here, okay, then we know it's actually bounded on the whole sector. Okay, and the bigger this gets, the less we know inside of the sector, the smaller the sector needs to become. Right? But this is not enough for us, because if you look now what we knew on the imaginary parts and the real parts, we have the bounds we want. Okay? So then we just need to fill the quadrants. All right? So we need an angle, okay, of pi over 2. But we don't have a boundedness on the border. We have some kind of boundedness by a function there. So we just needed to extend these results. And actually, we did it in a somewhat optimal way using these weight functions. So if I have a weight function satisfying first some preliminary conditions, but this is a bit stronger than being little o of t sigma, which is natural because of, remember, the epsilon we have there. This will have some, but we need a bit stronger so that you have actually functions you're working on somewhat, but don't mind that too much. But okay, then we know that equivalently we have this integral bound here on your weight function. This is equivalent to having a kind of Bragman-Lindelof principle on the sector of angle pi over sigma, but now we can have this bounds here, okay? And then this stays the same, and then we can conclude actually the bound holds everywhere on the sector. Right. Okay, and then you can go back. Yeah, I'll not give a sketch of the proof, but it basically boils down to having a good Poisson transform of your weight function. All right, and now we can show it very quickly, because actually, if you look at the condition, so if you want to show the first case where omega is t squared, note that this does not hold. Okay, so we cannot apply the Bragman-Lindelof principle on the whole sector, on the whole pi over 2. But what you just do, for instance, on this quadrant, so you make sector inside of the quadrant, okay, with some angle pi over 2 minus epsilon. This is epsilon. Epsilon, then you apply Bragman-Lindelof here. Lindelof here on the sector where you can bound it nicely, and then using what I said, we needed explicitly the bounds we had. So then you can close this sector, but here you can have, using again the bounds that we have explicit estimates, and then you just let the sector become bigger and bigger. Okay, and this is actually a bit how Hardy did it in his original work. Right, so and this is how you close the whole sector, and then you get your bounds on the Barkman transform, which was exactly what we needed. Right, so this gives us the result in one dimension, and then we can just apply the same, but now we don't have to care about these smaller angles, but because now we have weight functions that do, we assume, satisfy the condition, so we can do on the whole sector and then complete it and get our full characterization again in one dimension. And okay, so that's all good, but now what about multiple dimensions? So this at first was a problem for us. We didn't really know. The only thing we could say using the same, because you can, of course, have multiple dimensions of this Pragman-Lindelof principle, but then you needed to have more information on the Barkman transform side because you have to close the sector in multiple dimensions. Okay, and this is what we first saw that, on how to do this. So we needed information on the partial Fourier transforms. So we couldn't go back from here. We needed a bit more. But then, not so recently, okay, there is some idea we had that, okay, so if you have your weight function omega, and then you don't look at if you have an entire function, for instance, but you don't really look at the entire function in its whole stuff. You fix angles, but then in each of the variables, you have a bit of a weighted version of that specific complex function. So you define on the unit circle in d-1 dimension this complex function here, all right, using this weighted u1 and ud. So you change it all up a little bit, and you assume you have a uniform bound there with respect to the weight function, which is what we have actually, because these multiplication by elements in the unit circle, they remain invariant. If you have only real parts, then you'll remain only with real parts. If you only have imaginary parts, you only have imaginary parts. Okay, so this works, and then you can still close it down using the Pragman-Lindelof principle in one dimension. So we have this for our Barkman transform. Okay, but we have it for every u, and this was somewhat you had to see that you had to apply this to every u on the unit circle, and then from here, it's not so difficult. Yeah, you had to see it a bit to get to here. You can actually show that this is enough to already infer that you have these bounds on the zero, and it's the derivatives of f at zero. But this is, of course, exactly just the Hermite coefficients divided by some alpha factorial. Okay, and once you got this, and then you have everything you need. So that's how we could close it. But this is not published yet, so it's upcoming work. Okay, and I think with that I'll